Lecture 8 is Nucleophilic Substitution. This is Chapter 6 in Wade. We're going to be splitting Chapter 6 into two parts. The first part is going to be Nucleophilic Substitution, and the second part is going to be Elimination. Now, Chapter 6 involves 4 reactions, 2 of which are classified as Nucleophilic Substitution, and 2 of which are classified as Elimination. These 4 reactions in Chapter 6 constitute kind of their own little universe, and a lot of students get tripped up at this part in the course trying to navigate the relatively intricate and complex universe of these 4 reactions. These are classes of reactions, meaning they are a general kind of format or a general type of template that many other reactions follow, which means that we're going to be seeing more reactions throughout the class that use the mechanisms and principles that are highlighted in Chapter 6. So as we go through these reactions, keep in mind that they are general and that they can be applied in a wide range of contexts. So let's begin with nucleophilic substitution. This is a new reaction, and we're going to talk about a new principle called chemical specificity. So here's the nucleophilic substitution reaction. If you look at it, it's a very relatively simple looking reaction, when in fact it's one of the most useful reactions in organic chemistry, but it is exceedingly deceptive in its simplicity. So the general picture is that we've got a molecule with some group A, we react it with another molecule, something B, that has a lone pair and a negative charge, and the product has B substituted in place of A. So it's basically a substitution reaction. B is substituting A. Now, B, having a lone pair and a negative charge, can act as a Lewis base, or what we've called a nucleophile. It has a lone pair of electrons that it can donate. And we say that B displaces A, and A we would call a leaving group, simply because it leaves during the reaction. A is on the molecule, and after B displaces it, A leaves. So that's the general picture. Again, A could be a wide range of things. It could be an atom or a group of atoms. Again, B can be a wide range of things, except that B does have to have a lone pair and usually will have a negative charge. So looking at this reaction in its simplicity, what kind of questions might you want to ask when you think about this reaction? I'll give you a minute to think of some questions that you might want to ask somebody if you're going to be studying this reaction, and the answers that that question can provide might help you understand the reaction better. So here are some questions that I thought would be good to ask. The first thing, and maybe it's too obvious of a question, how does B minus displace A? And why does it displace A? That's always a good question. Why does this reaction happen, and how does it happen? So we are taking for granted here that B will displace A, but that means that first of all, B wants to go onto the molecule and A wants to come off of the molecule. So how does B displace A, and why does it do that? What makes A willing to leave? We said that A is a leaving group, but what does it mean to be a leaving group? What does a molecule have to be like or look like or behave like to be a good leaving group? That would be a great question to ask and get an answer to. Now, A minus, notice over here, A with a lone pair and a negative charge, looks like a nucleophile too. It looks just like B with a lone pair and a negative charge. So a good question to ask would be, does the reaction run backwards, or why doesn't the reaction run backwards? If A looks like a nucleophile, what's stopping A from displacing B and getting back to where we started? A little bit more sophisticated of a question, we have a stereocenter, or at least we potentially have a stereocenter. Notice that this carbon right here, carbon number 2, has a methyl group, an ethyl group, a B group, whatever B is, and probably a hydrogen. It's not drawn here, but it's likely to have a hydrogen. In this case, it does have a hydrogen. So this carbon right here is a stereocenter. So anytime that we are dealing with a stereocenter, we need to think about what stereochemistry is involved. Does it matter if these molecules are R or S in their stereocenters? Or if they start as R or S, do they finish as R or S? Do we keep the same stereochemistry, or do we invert the same stereochemistry? So what stereochemistry is involved? And another question, this is a leading question because it turns out this is a very important answer. Does degree of substitution on Ca matter? Does it matter if this carbon is a methyl carbon or a primary carbon or secondary or tertiary or allylic or benzylic, for instance? Does substitution matter? That's a good question to ask. So let's look at the mechanism. Remember, when we went through free radical chain reactions, we started with the overall reaction, kind of a general picture of it, and then we looked at the mechanism and kind of saw how the reaction proceeds. And we used that mechanism to help us predict what products would look like when we're starting with any novel or randomly selected starting material and reactants. So here's the mechanism. In the first step, the Lewis base or nucleophile donates its electrons into the carbon leaving group sigma star or anti-bonding orbital. Now there's a lot to say there. So this is what it looks like. So here's our molecule. It's a carbon with, say, 3 groups on it, X, Y, and Z. We'll worry about what X, Y, and Z can be later. But for now, we've got a carbon with 3 groups and a leaving group, L. In the first step of this mechanism, in fact, I'm going to tell you in a moment, it's the only step in this mechanism. The nucleophile donates its electrons, and specifically it donates them into the anti-bonding orbital of the carbon leaving group bond. Now, if you remember, the anti-bond is on the back side of the bond. If the bonding orbital is over here between the C and the L, the anti-bonding orbital is on the opposite side, the back side of that bond. So the nucleophile will always approach that carbon from the side that contains the anti-bonding orbital. Okay, second step. As the carbon leaving group antibonding orbital is populated, the nucleophile carbon bond is formed while the carbon leaving group bond is broken. So we are forming this bond from the nucleophile to the carbon, and we would get to a transition state that looks something like this. So as the nucleophile carbon bond is being formed, the carbon leaving group bond is being broken. There's a couple reasons for this. The first one is that carbon already has 4 bonds here. So when the nucleophile donates its electrons into that carbon to make a bond to it, carbon is getting a 5th bond. And remember, there is no room for a 5th bond on carbon. Carbon can only make 4 bonding orbitals at one time. So that's why as one bond is formed, as we are adding a bond, we are also simultaneously breaking another bond. And the bond that breaks is the leaving group bond. So it's leaving. Now, again, why does that happen? Because you might remember from general chemistry, when you populate an anti-bonding orbital with electrons, you weaken the corresponding bond. You might remember calculating bond order from molecular orbital diagrams, and every time you add an electron to an antibonding orbital, the bond order goes down. You go from, say, a bond order of 2 to a bond order of 1.5, and then if you add another electron in there, you go from a bond order of 1.5 to a bond order of 1. So as you add electrons to an antibonding orbital, you make one new bond, and that population of that orbital causes the bonding orbital to break. Then 3, the leaving group leaves, it takes off, and it takes the carbon leaving group bonding electrons with it. So we are showing here this bond being broken, and the electrons in that bond are going on to the leaving group. It's taking the electrons with it. So if we go back to our big template here, these electrons that A ends up with are the electrons that it was bonded to the carbon with. And the electrons that B donated are the electrons that it is bonded with. So I've listed this in 3 steps, but this really all happens in 1 step. I'm going to show you that in a moment, but we're going to say that as the nucleophile is adding its electrons in, the leaving group is taking its electrons away. That's happening in 1 step. I'm just breaking it into 3 logical kind of steps. So this is a little bit of an odd picture. What I'm showing here is the carbon leaving group bond. So here's the bonding orbital. You remember this is what bonding orbitals look like. They've got high probability of electron density between the atoms and low probability of electron density away from the atoms. That's a bonding orbital. This is what the anti-bonding orbital looks like. It has high density away from the atoms and no electron density between the atoms. So these are shown separately, but keep in mind that both of these orbitals are present kind of simultaneously. They overlap each other. They've just been separated here for clarity. So here comes the nucleophile with its lone pair of electrons, and it's going to donate its electrons into the antibonding orbital. It's been drawn here so that these colors are the same to show that they are in the same phase. Specifically, it's the HOMO of the nucleophile, the highest occupied molecular orbital of the nucleophile that the electrons are donated from. The nucleophile is going to use its highest energy electrons when it does the reaction, and we will see in a moment that the anti-bonding orbital of the carbon leaving group bond is the LUMO. The electrons go from the highest orbital in the nucleophile to the lowest orbital, the lowest unoccupied orbital, I should say, in the substrate, the carbon leaving group substrate. Specifically, let's look at this diagram. This is a molecular orbital diagram for CH3Cl. It's been simplified just to show the valence orbitals. But for CH3Cl, here we've got 4 sp3 orbitals from a carbon. And again, they're all the same energy. I've just separated them for clarity. So carbon brings in 4 sp3 orbitals, each with 1 electron. Then we have 3 hydrogen s orbitals, and those are 1s orbitals. So those are going to be low in energy. And we've got 1 chlorine sp3, which is a 3s orbital. So we have a higher energy electron coming from the chlorine and 3 lower energy electrons coming from the hydrogens. These 4 orbitals are going to mix with these 4 orbitals, and we're going to make 4 bonds. Now, the 3 orbitals that are mixed with the hydrogens are going to make lower energy bonds. Those are 3 CH sigma bonds. And the orbital that happens to mix with the chlorine orbital is going to give us a higher energy sigma bond. Now remember that in a molecular orbital diagram, the lower the energy the bonding orbitals are, the higher energy the antibonding orbitals are. So these 3 antibonding orbitals up here are the corresponding antibonding orbitals to these low energy CH sigma bonds. And this lower energy antibonding orbital is the corresponding antibonding orbital to this bonding orbital. So if we look at this molecule, where are the electrons from the nucleophile likely to go? They're going to go into the LUMO, the lowest unoccupied molecular orbital. So in CH3Cl, if the nucleophile donates its electrons into the lowest available orbital, that's going to cause the chlorine carbon bond to break. Populating the antibonding orbital causes the corresponding bonding orbital to break. So in this diagram, we can see that chlorine would be the leaving group. That's the bond that's going to break because it has the lowest LUMO, the lowest unoccupied molecular orbital. To give this in a more pictorial view, here's the carbon-chlorine bonding orbital. We've got high electron density between the atoms and low electron density away from the atoms. We look at the antibonding orbital. We have high electron density away from the atoms and no electron density between the atoms. So this green bonding orbital is this guy right here, the bonding orbital, and this red antibonding orbital is this guy right here. They are both present on the same atoms simultaneously. So if we look at them kind of superimposed on one another, this is what it looks like. So you can see that the nucleophile is going to fill the LUMO, which would be on the back side of the carbon-chlorine bond. Now, a question would be, why does the nucleophile go after the carbon and not the chlorine? Because they both have a lobe from the LUMO. There's a LUMO lobe off the carbon, and there's a LUMO lobe off the chlorine right here and right here. So why does the nucleophile go after the carbon side and not the chlorine side? Well, it would be because of the charge on the respective atoms. The nucleophile, with its lone pair of electrons and high electron density, would be attracted to the more positive end of this bond. Carbon-chlorine is a polar bond. We have a partially positive carbon and a partially negative chlorine. So the nucleophile is going to be attracted to the carbon's LUMO because the carbon has a positive charge. The big picture then is that the nucleophile adds to the antibonding orbital, which is on the back side of the bond. It's attracted to the carbon side of that bond because carbon has the partially positive side, chlorine has the partially negative side. And by populating the antibonding orbital, we cause the bonding orbital to break, and the electrons then go on to chlorine, as chlorine is seen as the leaving group. Also, we are making a fifth bond by adding that nucleophile in. So we have to break a bond so that we don't overfill carbon's valence. To show this in a three-dimensional view, here's an example of a nucleophile. This is CH3SH, methyl sulfide. And here's CH3I, methyl iodide. So this is going to be our nucleophile. This is going to be our substrate. The nucleophile is going to donate its electrons to the carbon, and we're going to be making a bond in green. While that bond is forming, we're going to be breaking this bond in red. And as the bond is formed and broken, eventually the leaving group leaves. I'll show you that again. Here's our first step. Our initial conditions. The nucleophile attacks, the bond is formed, a bond is broken, and the leaving group eventually leaves once the added bond is fully formed. Now I want to show you something very subtle here. Notice the stereochemistry, or at least look at the three-dimensional orientation of this group. Now, this actually doesn't have stereochemistry because it's an iodine and 3 hydrogens, so we don't have 4 dissimilar groups. But look at how this is oriented. We've got the 3 hydrogens kind of pointed towards the left, and we've got the iodine pointed towards the right. As the bonds are broken and formed, notice what happens to these hydrogens. They flatten out. We get this kind of nearly octahedral shape. This is trigonal bipyramidal geometry, if you remember Vesper, but these atoms flatten out. And once this bond is formed in green and this bond is broken in red, look what happens to the hydrogens. They've actually inverted. The hydrogens on this carbon, or the groups on this carbon, again, they don't have to be hydrogens, but the groups on this carbon invert. We start with one orientation. As the bond is formed, they are kind of flattened out, and as the bond is broken, they invert. That's very important. Let's look at some details related to what we've mentioned. So the first step, again, the Lewis base, the nucleophile, donates its electrons into the carbon leaving group antibonding orbital. There are some requirements for that. It can't just do it willy-nilly. It has to be some specific conditions met. The Cl, the carbon leaving group bond, must be polar. That is to say, L, the leaving group, must be more electronegative than the carbon. This creates a delta plus charge on carbon like we saw, and a delta negative charge on the leaving group. Therefore, the nucleophile would be attracted to the carbon. If the nucleophile is not attracted to this carbon, the reaction is not going to happen. Again, we specifically need the nucleophile to attack the carbon and displace the leaving group. So there must be some motive for the nucleophile to do that, some attractive force. And we have that attractive force by ensuring that carbon is partially positive. And we can ensure that carbon is partially positive by having it bonded to an atom that is more electronegative than it. Secondly, the sigma star orbital, the antibonding orbital into which the nucleophile donates its electrons, must be sterically accessible. Steric means related to bulkiness. So X, Y, and Z cannot be bulky groups. If X, Y, and Z are very bulky, the nucleophile will not be able to access that antibonding orbital. Back to this picture here, where the nucleophile is donating its electrons into the antibonding orbital here, into the backside of this carbon-iodine bond. If these three groups right here are really big and bulky, the nucleophile is not going to really see that carbon. That carbon's going to be blocked off by these big groups. So this carbon needs to be sterically accessible, which means that these groups need to be relatively small. So keep that in mind for the attacking phase. We say the nucleophile attacks this carbon. The attacking phase, we need to have a delta positive carbon, a delta negative leaving group, which is caused by the leaving group being more electronegative, and X, Y, and Z, whatever these other groups on the carbon are, need to be relatively small so that the nucleophile can actually find its way into that carbon. The second step to keep in mind, that as the carbon leaving group antibonding orbital is populated, the nucleophile carbon bond is formed while the carbon leaving group bond is broken. So what is required for that? First of all, populating the carbon leaving group antibonding orbital must cause carbon's valence to be exceeded. So if carbon only has 3 bonds, for example, then when the nucleophile adds its electrons in, we're only making a 4th bond. So in that case, nothing needs to leave. In order for a leaving group to leave, the addition of these electrons must cause carbon's valence to be exceeded. So in response to that valence being exceeded, the leaving group leaves and takes its 2 electrons with it, so breaking the carbon leaving group bond, and therefore maintaining carbon's valence at 8 electrons. So if carbon's valence is not exceeded for whatever reason, the nucleophile carbon bond can form, but nothing needs to leave, and therefore it's not a substitution reaction. If nothing is being substituted, it's not a substitution reaction, so that would be a different reaction. This specifically requires that carbon's valence be exceeded, and a leaving group leaves as a result of that. Okay, looking at the leaving phase, the leaving group leaving, what are the requirements for that? Well, because L is electronegative, we already said that, L needs to be electronegative so that it gives carbon a partially positive charge. Because L is electronegative, it needs to be electronegative enough to be stable with that negative charge. So notice that when L leaves and takes the electrons with it, it ends up with a negative charge. So in order to make these products stable, we want our leaving group to be very electronegative. We would call that a good leaving group. A good leaving group is something that is very stable with the electrons that it gains and hopefully a negative charge. So the kicker is that L minus, the leaving group all by itself, must be more stable than the nuc minus, so the nucleophile all by itself. Notice that in order for that to be the case, L needs to be more electronegative than the nucleophile, or at least more stable with the negative charge, perhaps maybe from resonance or some other stabilizing factor. But having L be more stable than nuc with the negative charge means that our product is more stable than our reactant. That ensures that our reaction goes forward and not backwards. If the nucleophile were more stable by itself than the leaving group was, then the reaction would run backwards, or the reaction would just not proceed at all. So, what are good leaving groups? What kind of groups work as being leaving groups in this reaction? Well, things that are stable with negative charges. So, for example, chlorine, bromine, iodide, or chloride, bromide, or iodide, the negatively charged halides. Those are the most electronegative groups or atoms on the periodic table. So those are going to be very good leaving groups. Weak bases. Weak bases are just molecules or atoms or ions that are stable with a negative charge and don't want to give that negative charge up, or don't want to give up their electrons. So what about sulfonate, O3Sr, or sulfate, SO4R, or phosphate, PO4R? Why are these stable? Well, they have negative charges on the oxygens. That's pretty good since oxygen is fairly electronegative. But resonance, sulfonate has 3 resonance structures. Sulfate has 3 resonance structures. Phosphate has 2 resonance structures. That these negative charges can be delocalized over other oxygens. That gives stability to these charges, whereas chloride, bromide, and iodide have a full negative charge. Each of these oxygens on sulfonate or sulfate only have 1/3 of a negative charge. And on phosphate, these oxygens only have half of a negative charge. So that makes them more stable. Also, neutral molecules can be good leaving groups because neutral molecules are stable. So stable neutral molecules like water or alcohols or amines or phosphines or sulfides. The oxygen here in water and alcohol, or the nitrogen or the phosphorus or the sulfur, these atoms are stable with a lone pair when they're neutral. So those would be good leaving groups. If we can kick water off of a molecule and use water as a leaving group, that reaction is very likely to proceed because water would be a stable product. So here are some other interesting properties of the reaction. The first one is that, like we said before, the reaction occurs in one step. This is kind of shown as 2 steps, where the nucleophile adds, we get to this transition state, and then the leaving group leaves and we get to our product. But like I said, this happens in one step. As the nucleophile is adding its electrons in, the leaving group is leaving simultaneously. We say it is one concerted step, that the nucleophile carbon bond is formed at the same time or in concert with the carbon leaving group bond being broken. One concerted step. So it's a one-step mechanism. We learned a 3 or 4-step mechanism for free radical halogenation. This reaction, this substitution reaction, is just one step. Now, because that one step in the mechanism involves both the nucleophile and the substrate, we would say that the rate equation is second order. We say that the rate equals K, some rate constant, times the concentration of the substrate, whatever this guy is, times the concentration of the nucleophile. The rate limiting step, the one step in this reaction, is the rate limiting step, and the rate limiting step involves two species. So we would say this is a second order reaction. In fact, this reaction is called SN2. That stands for substitution, nucleophilic, second order. Another important feature, and this is a really important feature in fact, is that the stereochemistry at the attacked carbon is inverted. We said that this nucleophile adds by what we call backside attack. It attacks the carbon from the backside of the leaving group bond. And as a result of that, the stereochemistry is inverted. Let me show you this. Let's just imagine that the stereochemistry of this carbon has 4 dissimilar groups, and those 4 dissimilar groups can be ranked as leaving group is 1, X is 2, Y is 3, Z is 4. So look what happens as we add the nucleophile and displace the leaving group. Remember how the 3 other groups kind of flattened out? We started with them pointed towards the nucleophile like this. Again, since the nucleophile is adding from the back side of this bond, these groups would be pointed towards the nucleophile. As that nucleophile adds the bond, these groups flatten out, and then when the bond is fully formed and fully broken, they pop the other direction. It's kind of like an umbrella popping out of plane, an inverting umbrella. So if we have this ranking here, we add the nucleophile, these groups flatten out, and then they pop the other direction. Now, if the nucleophile is the highest group, and I'm telling you it almost always will be, look what happens to our stereochemistry. 1, we start going from 1 to 2 to 3 to 4 is counterclockwise. In our product, going 1 to 2 to 3 to 4 is clockwise. So we have inverted the stereochemistry. Backside attack causes that, and we get kind of that inside out umbrella. The umbrella pops inside out. Because of the fact that the antibonding orbital needs to be accessible by the nucleophile, the reaction favors methyl leaving groups. So a leaving group on a carbon with 3 hydrogens on it would be a methyl group, a methyl leaving group on a methyl. Favors methyl carbons over primary carbons, over secondary carbons, over tertiary carbons. The smaller our groups are on this carbon, the better. So the fewer carbons that are attached to our attacked carbon, the better. So methyl would mean that X, Y, and Z are all H's. Now let's think about that. There's a lot going on here. Not only is that a more accessible carbon because its groups are small, but there's also no hyperconjugation. Remember, we talked about the stability of charges on a carbon, that positive charges are stabilized by hyperconjugation because that hyperconjugation overlaps with that positive charge and kind of masks it, makes it less positive. So if we have a methyl group, if this carbon is a methyl group, so X, Y, and Z are hydrogens, and there's no hyperconjugation, because these are hydrogens, that means that carbon's delta plus is most significant. There's no electron orbital overlap that can cover up this partially positive charge. And remember that we need that partially positive charge in order for the nucleophile to be attracted to this carbon. So in addition to the carbon being sterically accessible, it also will have the most positive charge on it. If, on the other hand, at the other extreme end of this continuum, we have a tertiary carbon, so meaning that X, Y, and Z are also carbons, we've got lots of hyperconjugation from the overlap of these groups. If you don't remember hyperconjugation, go back and look at your notes. Make sure you understand that. In addition to more hyperconjugation, that means that not only are carbon's delta positive charge least significant because it's blocked off or it's covered up by these three other groups, but carbon is also the least sterically accessible in that case because the carbons and their corresponding bonds are big and bulky. Now, this reaction does not occur for tertiary leaving groups. It turns out that since this is a continuum, that once we go beyond a secondary carbon and move towards a tertiary carbon, carbon becomes too inaccessible by the nucleophile for the reaction to take place. In fact, secondary leaving groups are kind of the extreme end of it. A leaving group on a secondary carbon just barely works for this reaction. Methyl is awesome. The reaction happens very good for methyl groups. For a primary leaving group, it still works pretty darn well. For secondary, it's really starting to slow down. And by tertiary, the reaction doesn't happen at all. So let's look at a reaction. Here's a reaction where we have a nucleophile, something with a lone pair and a negative charge, and a substrate. Our substrate happens to have a bromine on it. And in this reaction, the nucleophile is going onto our substrate, and it is displacing bromide on our substrate. So let's look at this reaction from the perspective of our mechanism. Do we have a polar bond? That is to say, do we have a location on our substrate where carbon will be positive or partially positive, and the nucleophile with its lone pair and negative charge will be attracted to that carbon? Well, indeed we do. That carbon is way less electronegative than the bromine is. So this carbon-bromine bond is polar. Bromine is the negative end. Carbon is the positive end. So there's our polar bond. We have a nucleophile, like I pointed out. We have a group with a lone pair and a negative charge. So what's our leaving group? Remember, the leaving group would be the bromine. It's the electronegative group or atom that's attached to our carbon. So bromine is our leaving group, and indeed you see that in this reaction, bromine leaves. Let's look at our stereochemistry. Do we have the proper stereochemistry here? Bromine is drawn as a wedge, so the carbon-bromine bond is coming out towards us. That means that the anti-bonding orbital is behind the molecule. So when this reaction occurs, if it occurs by an SN2 mechanism, the nucleophile needs to attack from the back side of this carbon-bromine bond. Look at where it is on the product. The OH is attached from the back side. It's now going away from us. So indeed, we have inverted our stereochemistry. We've inverted our stereocenter. If we were to rank these groups, bromine would be 1, ethyl would be 2, methyl would be 3. So it's going in the R direction. the hydrogen's going away from us. So this is an R stereocenter. Here, oxygen's the number 1 group. Ethyl would be 2, methyl would be 3. Hydrogen is 4th. It's coming towards us. So we're going in the R direction, but since hydrogen is coming towards us now, this is actually S. So we have indeed inverted our stereocenter. Is L more stable than the nucleophile? Yes, indeed. Bromide is more stable than hydroxide. Hydroxide is a strong base. Bromide is the conjugate base of hydrogen bromide. Hydrogen bromide is a strong acid. So the conjugate base of a strong acid would be a weak base. So bromide is a weak base, which means it's stable. Hydroxide is a strong base, which means it's unstable. So our leaving group is more stable than our nucleophile. How about the accessibility of our sigma star? What's the substitution of the carbon bearing the leaving group? This is a secondary carbon. It has a methyl group on it and an ethyl group on it. It has 2 carbons attached to it. So this is a substrate that fits into the requirements for our SN2 mechanism. It's again, secondary is on the kind of extreme end of our range, but it still should work. Tertiary doesn't, but secondary does. Another thought, is our nucleophile big or small? OH- is a relatively small molecule. Oxygen's not that small of an atom, but comparatively speaking, compared to our substrate, which has 1, 2, 3, 4 carbons, a bromine, 3, 5, 8, 9 hydrogens, all those atoms on it, OH- is pretty small. That's important because the reaction requires that the nucleophile be able to access that antibonding orbital. So not only would be the substitution of the carbon matter, but the size of the nucleophile should matter as well. If our nucleophile is huge, big, and bulky, it's going to have a harder time accessing that antibonding orbital. And since we are already at a secondary degree of substitution, we are already fairly blocked off here. The methyl and the ethyl group serve fairly well to block off that antibonding orbital. Again, it still should be able to reach it, but just by virtue of having a small nucleophile, we can feel fairly confident that it would be able to. Just to reiterate, what do I mean by inverting the stereocenter? Like I said here, this bromine being a wedged group kind of coming out at us means that this stereocenter is R. And this hydroxide therefore needs to add from the back side. The requirement is that it adds from the back side. So if the bromine is coming towards us, the back side is the OH going away from us. So we now have an R in our reactants and then an S in our products. So the stereochemistry is inverted. If we have only R's in our reactants, meaning that we have an enantiomerically pure substrate, only R's, our products will have only S's. We call this reaction stereospecific. Remember that on the first slide, we were going to introduce a concept called chemical specificity. This reaction makes a specific product from a specific reactant. Recall when we did free radical halogenation, we said that the radical could add from either face of our carbon, which means that if we start with, say, butane and we're adding a chlorine, we could get R2-chlorobutane or S2-chlorobutane. Free radical halogenation is not stereospecific. It makes 2 products from one reactant. The SN2 reaction is stereospecific. We get one specific product from one specific reactant. An R will turn into an S specifically. An S will turn into an R specifically. Kind of just to reiterate this, the OH minus is going to attack from the back side. So if the front side bromine is on the right over here, the OH is going to attack from the back side on the left. That's going to invert our groups, and we go from R to S. I want to point out a caveat to this reaction. Remember that by definition, nucleophiles are bases. A Lewis base is a base, and nucleophiles, aside from acting as a Lewis base, can also act as a Bronsted-Lowry base. Look at our substrate here. Here we've got 4 carbons with a chlorine and a hydroxide, an OH group. And we've got a nucleophile here, Na plus OCH3 minus. So this OCH3, this oxygen, has a lone pair, and therefore that's why it has a negative charge. It needs a sodium or some cation to balance that charge, and we're going to dissolve it in methanol, CH3OH, just because ionic compounds are salts. They're ionic and not particularly soluble in organic liquids or organic solvents. So we're going to use a very polar solvent like methanol to get this guy to dissolve. But anyway, this is our nucleophile. Now, if you look at our substrate, where's the good leaving group? If we go back and look at our leaving group chart, chloride is a good leaving group. You don't see hydroxide anywhere here. Hydroxide is not a good leaving group. And remember, we looked at this here. Hydroxide's a strong base. Hydroxide's a nucleophile. It wants to go on. It wants to donate its electrons to make a bond. It doesn't want to take its electrons off and break a bond. So looking at this substrate, chloride is a better leaving group than hydroxide. So if our nucleophile acts as a nucleophile, what's it going to do? It's going to attack this carbon because that's partially positive. That chloride would be negative. So we have a polar bond. The nucleophile would donate its electrons to the carbon. That would exceed carbon's valence. It would cause the carbon-chlorine bond to break. Chloride would leave, and we would have substituted OCH3 in place of that chlorine. Our byproduct would be sodium chloride. Then the chloride would simply pair up with the sodium. That's what this reaction would look like if our nucleophile acts as a nucleophile. However, like I said, nucleophiles can also act as a Bronsted-Lowry base. So notice that we've got a acidic hydrogen on this OH group. That hydrogen is on a very polar bond with the oxygen, and therefore it's acidic. So if our nucleophile acts as a base, we just do a acid-base hydrogen proton transfer. The nucleophile or base would grab the H from our hydroxide group, deprotonate the O, we end up with O minus and A plus, and we just make some more methanol. So here's the kicker. Bronsted-Lowry acid-base reactions occur faster and or more readily than substitutions do. What I'm saying is that this reaction, or the reaction proceeding in this fashion, where our nucleophile acts as a Bronsted-Lowry base, is more likely to occur. It's going to occur faster than our top reaction is. So that means that if there are any acidic hydrogens present on our substrate, then the nucleophile will extinguish itself by acting as a Bronsted-Lowry base, and no substitutions will take place. So if we have this substrate with a nucleophile, the nucleophile will not substitute the chlorine. It will simply deprotonate the OH, and we won't get a substitution. The base reaction, the Bronsted-Lowry reaction, occurs faster than the Lewis reaction. I want to point something else here. I've drawn this specifically, this OH as a wedge, meaning that this is going to be in the R configuration. If you want to prove to yourself that this is R, you can do that. This is in the R configuration. Since the substitution is not occurring at this carbon in this hypothetical reaction, the substitution is occurring at this carbon, which I've drawn as a straight line. Remember that a straight line indicates that we are not specifying whether it is R or S, which then implies that it is both. There's a mixture of R and SR molecules here. And so think about it. Since SN2 reactions require inversion, anything that's an R will turn into an S. And anything that's an S would turn into an R. So we have a mix of R or S at this stereocenter, and therefore we end up with a mix of R and S at this stereocenter. Since this stereocenter here is not inverting, it's not reacting in an SN2 reaction, it's not getting attacked by that carbon, it's not going to invert. So if it's R in this case, it's going to be an R in this case. But the big picture here is that in this context, it doesn't matter. That top reaction would not ever occur because we have an acidic hydrogen present. Having this acidic hydrogen present ruins the SN2 reaction. The mechanism does not proceed in that way. Rather, we just do a Bronsted-Lowry proton transfer. Let's think about the strength of our nucleophile. Here we've got two reactions, fairly similar. In one case, we've got our substrate, 2-chlorobutane, with sodium methoxide. So this is Na+, OCH3-. Again, this is an ionic compound, which means we'll probably need some kind of solvent to help it dissolve. In this case, we're just using methanol. So these are different nucleophiles. Why are they different? They're really similar. One of them's got the Na+, which is ionically bonded to the O-. In this case, we've got the H, which is covalently bonded to a neutral oxygen. This oxygen has lone pairs in both cases. It's got 3 lone pairs in the ionic sense, and it's got 2 lone pairs in the covalent sense. Which of these nucleophiles is the strongest? If your answer was the methoxide, you're right. Having 3 lone pairs and a negative charge versus 2 lone pairs and no negative charge means that our 3 lone pairs and our negative charge oxygen is going to be more willing, more likely to donate its electrons. Let's think about how this reaction will proceed. Our oxygen is going to be attracted to the carbon that has a partially positive charge on it that is resulting from being bonded to a chlorine. So the oxygen will donate its electrons to the backside of the carbon-chlorine bond. That's going to exceed the valence. The electrons are going to go onto the chlorine. That bond is going to break, and we will be forming the OCH3 bond. We are then displacing the chloride. We end up with Na plus Cl minus. Again, chloride is a good leaving group. Let's compare it to this case. With the O neutral, has 2 lone pairs. It's going to donate one of them to the carbon. That's going to exceed the valence of that carbon. The chlorine is going to leave as chloride. But look what happens here. Our oxygen already has a bond on it. It's got 2 bonds, in fact. And so we're making a 3rd bond to our substrate. That's going to give oxygen a positive charge. Remember, oxygen with 3 bonds and 1 lone pair has a positive charge. So, which reaction is more favored? It's going to be the top one, but for 2 reasons. First of all, we have a better nucleophile. We have a negatively charged nucleophile as opposed to a neutral nucleophile. Secondly, our products are more favorable. We've got a neutral substrate and our negative leaving group. Versus here, we have a positive substrate. In fact, our positive charge, our formal positive charge, is on the oxygen. Oxygen does not want to be positive. In fact, it wants to be negative, if anything, but it wants to be neutral or negative. So if our choice is using a good nucleophile and getting neutral products and negative products versus using a neutral nucleophile, a weaker nucleophile, and getting charged products, not so good. The rule is that a base is always a stronger nucleophile than its conjugate acid. So HOCH3 is the conjugate acid of OCH3-. Remember, the conjugate acid is what you get basically by adding a hydrogen to something. So the rule that a base is always a stronger nucleophile than the conjugate acid means that this guy is going to be better nucleophile than this guy. I want to point out here that we have made an ether functional group. This is carbon, oxygen, carbon, or ROR. It's an ether. In fact, this is called methyl secbutyl ether. We'll talk about ethers in a little bit, in a few chapters. But we've changed our functional group. We started with an alkyl halide, which, by the way, we know how to make. We know how to make 2-chlorobutane. You start with butane and do a free radical halogenation with chlorine, Cl2, and light, and you get 2-chlorobutane. If we start with butane, do a free radical halogenation, we get 2-chlorobutane. We react it with sodium methoxide, and we get the displacement product, the substitution, and that is an ether. We've converted butane to an alkyl halide, and we've converted the alkyl halide to an ether. Let's talk about strength of nucleophiles. I've mentioned a couple things regarding what makes a nucleophile good or bad. First of all, it's got to be a charged molecule. A charged negative nucleophile is better than the conjugate acid, like we just saw, which would be neutral. We need a lone pair, at least 1 lone pair. The more lone pairs, the better, because that makes it more negative and therefore more willing to give up some electrons. They also need to be small. Remember that they have to be able to access that antibonding orbital, which may or may not be blocked off by any number of groups on the carbon bearing the leaving group. So small, highly charged molecules with lots of lone pairs and negative charges are good nucleophiles. So this is triethylphosphine, P with a lone pair. Here's SH-, sulfur with 3 lone pairs and a negative charge. Iodide with 4 lone pairs and a negative charge. Here's diethylamine, nitrogen with a lone pair. Here's a nitrile or a cyano group. a carbon with a negative charge in a lone pair. Hydroxide, oxygen with 3 lone pairs and a negative charge. Methoxide, oxygen still with 3 lone pairs and a negative charge. We don't want to make these too bulky, so we don't want too much on the negatively charged atoms. But relatively small groups are fine. Methyls and ethyls. Moderate nucleophiles, things that are a little bit weaker, might be bromide, ammonia, neutral, okay? Dimethyl sulfide, again neutral, chloride. And then weak nucleophiles are things that are very stable. So F-, very electronegative, not willing to donate its electrons. Here's acetate, resonance stabilized oxygen. Water, stable neutral molecule. Methanol, stable neutral molecule. There's something interesting here. Did you notice it? Iodide. If we go back and look at our slide that mentioned leaving groups, here's iodide. Weak bases are good leaving groups. Iodide is a weak base. So if iodide is a good leaving group, how could it also be a good nucleophile? Those are opposite things, remember. Leaving groups take the electrons and come off the molecule. Nucleophiles donate electrons and go onto the molecule. So there's something weird going on here. Also, bromide is listed as a moderate nucleophile, even though above it was listed as a pretty good base, as a weak base, as a good leaving group. Same with chloride. Also listed as a moderate nucleophile, but also listed as a good leaving group. So there's something fishy going on with the halogens. Chloride, bromide, and iodide somehow managed to be good leaving groups, weak bases, and strong to moderate nucleophiles, so strong to moderate bases. There's something weird going on there. Your book has these trends here. Remember we said that a base is always a better nucleophile than the conjugate acid. So hydroxide would be better than water. Again, negatively charged versus neutral. Sulfide would be better than hydrogen sulfide. So SH- would be better than H2S. NH2- would be better than NH3. Nucleophilicity also decreases as you get more electronegative. Remember that electronegative atoms want to hold on to their electrons, but a nucleophile should want to give it up. So N would be a better nucleophile than O, which would be better than F. Negative N would be better than negative O, which would be better than negative F. Neutral N would be better than neutral O. P would be better than S. Again, S is more electronegative than P. O is more electronegative than N. F is more electronegative than O, which is more electronegative than N. So nucleophilicity decreases with increasing electronegativity. That's the opposite of a leaving group again. Remember that more electronegativity makes a better leaving group. So all these trends that we're seeing, what's good for a nucleophile is bad for a leaving group. A good leaving group is a bad nucleophile, and a good nucleophile is a bad leaving group. The one weird exception are the halogens, because halogens we saw are also good leaving groups. They're electronegative. So how could they be good nucleophiles? It has to do with something that we call hardness and softness of the valence shell. So fluoride, having fairly small orbitals, fluoride just has the 2s and 2p's in the valence, versus iodide, which has 5s and 5p in the valence. Fluoride is also more electronegative than iodide. So fluoride has small orbitals, and the electrons in those small orbitals are being held very tightly. That's going to make the valence shell hard. That's not going to be very soft and squishy. There's going to be very little ability for that orbital to smear out and kind of reach into that antibonding orbital. The book refers to it as a back lobe. I'm calling it an antibonding orbital because that's what it is. But if the job of the nucleophile is to reach that antibonding orbital, which may or may not be blocked by these groups, a hard, small valence shell is not going to be very good at that. Fluoride is not going to be very willing to let those electrons smear out. They're being held very tightly. Iodide is the opposite case. Iodide has a huge, big, squishy, electron-filled valence shell. There are 53 electrons in iodine, so 54 electrons in iodide. Lots of electron density here that can kind of be smushed and spread out. So we can get more bonding from iodide because it can smear out its big, squishy, soft, large valence shell and reach that antibonding orbital. So fluoride is not a good nucleophile, but bromide and iodide are pretty good. Iodide is a strong nucleophile. Bromide and chloride are moderate nucleophiles because they have relatively big squishy electron shells. Fluoride is weak as a nucleophile, not good at smearing out its electron density. I've already mentioned this, but I want to reiterate it. That strength of the nucleophile also has to do with sterics. Sterics are important on the substrate, we said, because the sigma star must be accessible and not blocked off by big bulky groups. But they are also important for the nucleophile. The nucleophile must not be sterically hindered. We want our nucleophile to be small like a bullet, or long and kind of narrow like an arrow. Something that can very easily kind of sneak its way into that antibonding orbital and kind of miss those groups on the carbon that may or may not be blocking that antibonding orbital. So here's tert butoxide. It's a tert butyl group. Remember what tert butyl group looks like? With an O-, tert butoxide. It's a great base. It's a very electron-rich base. This oxygen not only has 3 lone pairs and therefore a negative charge, but also this big blob of electron density in the tert butyl group. So it's a really great base, but it's a bad nucleophile because it's very bulky. It's big and cumbersome and would have a very difficult time reaching into that blocked off antibonding orbital. Here's ethoxide. Similar to tert butoxide, you can see the similarities. It's got an O-, also 3 lone pairs and a negative charge. So it's got less electron density around it though, because it doesn't have as big of a blob of electron density from the T-butyl group. The ethyl group is much smaller. So it's not such a great base because it doesn't have so much electron density, but it turns out to be a better nucleophile than tert butoxide. And our explanation for that is that it's less sterically hindered. It's smaller. So higher electron density on the oxygen, but sterically hindered. It will just act as a base and grab an H+, a Bronsted-Lowry base. Ethoxide has lower electron density, but minimal steric hindrance, and therefore it will act as a nucleophile. So hopefully you're seeing that there are three things that are going on here. From the perspective of the nucleophile, it must not be bulky. It must have significant amount of electron density, and it must be more reactive than the leaving group. Those are the three important factors of the nucleophile. It needs to be small, with electron density, negative charge, lone pairs, and more reactive than the leaving group. From the perspective of the substrate, Cl must be polar. That ensures that our carbon is positive, partially positive, and so the nucleophile will be attracted to it. L must be electronegative, so that it's willing to leave. When it leaves, L must be more stable than the nucleophile, and the Cl sigma star, the antibonding orbital, must be sterically accessible. So methyl, primary, and maybe secondary, as long as our nucleophile is small enough. Additionally, we can't have any acidic hydrogens on our substrate, because if we have any acidic hydrogens, remember, the nucleophile will act as a Bronsted-Lowry base instead of a Lewis base, because Bronsted-Lowry proton transfers occur faster than nucleophilic substitutions. I've also referenced solvent a little bit. The solvent must be aprotic. What that means is that it can't have any acidic hydrogens on it. That is the same logic as why the substrate can't have any acidic hydrogens on it. If there are acidic hydrogens around, whether they are on the substrate or on the solvent, the nucleophile will go after those hydrogens. It also needs to be a polar solvent. That will aid in mixing the nucleophile and the substrate. Back here, I showed you two scenarios. It was here actually. I gave you two scenarios. And in this scenario, we had methoxide, sodium methoxide, an ionic compound. Ionic compounds are not soluble in organic compounds like this. So we need a solvent that is polar enough to dissolve both. It's polar enough to dissolve the nucleophile, which is ionic, but also organic enough to dissolve our substrate. Now, you're probably saying, Dr. DeHorst, this is a protic solvent. It's got an acidic hydrogen on it. So why are we allowed to use a protic solvent when you just told us that we can't have any acidic hydrogens around? Here's the answer. The reason we can get away with using a protic solvent here is that if our nucleophile grabs the H from our solvent, we just remake our nucleophile. The OCH3 minus turns into HOCH3, and the HOCH3 turns into OCH3 minus. So it doesn't change the equation at all. We don't really lose our nucleophile. If our nucleophile goes after that H, we just make a new nucleophile as a result of that. So there are some tricks that we can use in the event that we actually need a protic solvent, but in general, you want a polar solvent to aid in mixing that is aprotic, non-hydrogen bonding. We want to avoid interaction or complexation with the nucleophile. We want the solvent to help dissolve the nucleophile, but we don't want the nucleophile to be more attracted to the solvent than it is to the substrate. So keep these three things in mind. Now, what about tertiary? We mentioned that the reaction does not occur under SN2 conditions with a tertiary substrate, a leaving group on a tertiary carbon. Remember why? There were two reasons. The first reason was that the carbon antibonding orbital, the carbon leaving group antibonding orbital, is not accessible when there are three other carbon groups. We've got a methyl, an ethyl, and an isopropyl group here. Those are large enough, bulky enough, so that our nucleophile, even a small one like methoxide, can't reach it. Additionally, with these three carbon groups on our carbon of interest, we get three sources of hyperconjugation, and that hyperconjugation occludes, blocks off, and neutralizes any positive character on that carbon, which means the nucleophile won't find it. So if we try to do a SN2 reaction using SN2 conditions, so we'll take our substrate, a nice, strong, small nucleophile, and a polar aprotic solvent, THF. This is called tetrahydrofuran. That's what it looks like here. It's a polar molecule, but no acidic hydrogens. We won't get a reaction. Didn't work. We will not be able to substitute our methoxide in place of the chlorine. So are we stuck? Can we do anything with this? Well, not with SN2 conditions, but we can do something else. If we add silver chloride and heat to this reaction, something does happen. Look what happens. We do get substitution. We get our nucleophile, our OCH3, adding to our carbon, kicking off the chloride leaves. But here's an observation. If we start with one specific stereocenter, if we start with this stereocenter in this configuration, the chlorine would be 1, isopropyl would be 2, ethyl would be 3, methyl would be 4. We are going in the R configuration. If we start with the R, if this were an SN2 reaction, we should get all inversion. The OCH3 should add from the back side, which means that this product is the only product we would get if this was SN2. We also get this product. What does this look like? Notice that the OCH3 is on the same side as the chlorine was. That looks like front side attack, not back side attack. This product is impossible to form in an SN2 reaction. This one here is possible to form in an SN2, but not this one. So the fact that we are making two products means that we lose our specificity. SN2 is a stereospecific reaction. So this is not a stereospecific reaction. It's not SN2. It's something else. Here's an observation. If we triple the concentration of R 3-chloro-2,3-dimethylpentane, this guy right here, the rate triples. Okay, so the rate depends on the concentration of our substrate. If you recall, the rate depends on the concentration of the substrate and the concentration of the nucleophile in an SN2 reaction. It's second order. So that's great. If we triple our concentration of our substrate, the rate triples. If we triple the concentration of our nucleophile, sodium methoxide, the rate doesn't change. Aha! That means that our rate is only dependent on our substrate, not the nucleophile. This is not a second order reaction anymore. It's a different mechanism. Something else is going on. Additionally, we notice that our substrate reacts to give a racemic mixture of the R and the S, whereas SN2 should only give the S if we start from R. The mechanism has changed. This reaction is no longer SN2. Here's what the reaction looks like. This is an SN1 reaction. It's first order. It's first order in our substrate, zero order in our nucleophile. So this is a first order reaction. We're going to call it SN1. Here's how the mechanism works. Rather than the nucleophile attacking first and then the leaving group leaving as a result of that, kind of simultaneously, in one step, in the SN1 reaction, the leaving group leaves on its own. The rate limiting step only involves the substrate. It's the first step in this mechanism, and it only involves the substrate. The leaving group leaves on its own without any influence from the nucleophile. That generates a cation. We're losing a bond to our carbon. And as a result, we have a planar tertiary carbocation. Since this is sp2, it's going to be planar, and that means that the nucleophile can add from either face. It can add from the top face, in which case we would get this product over here, the retention, not the inversion product, but the retention product. Or it could add from the backside, from the underside, and we get the inverted product. This is really, really, really important, because even though we get a product that looks like the SN2 product, because this is tertiary, we should know that the nucleophile would not be able to access that antibonding orbital and force off the carbon. So the carbon force off the chlorine. So this molecule just sits there. The nucleophile can't do anything about it, but eventually the chlorine will leave on its own. Why would the chlorine leave on its own? The reason a chlorine would leave on its own is because the resulting cation is tertiary. Remember that tertiary cations are very, very stable. So there's motivation for that chlorine to leave. In an SN2, let's go back to SN2 for a minute. In SN2, if X, Y, and Z were hydrogens, and that leaving group were to leave on its own, we would get a methyl carbocation, which is very unstable. So, under the conditions that are good for SN2, SN1 is very bad. And under the conditions that are very good for SN1, SN2 is very bad. Basically, when SN2 can't happen, SN1 can. SN1 is also called solvolysis, which kind of means splitting by solvent. Lysis means splitting. So splitting by solvent. Usually in SN1, the solvent is the nucleophile. So we call it splitting by solvent. So again, here's our mechanism. SN1, the leaving group leaves first. Leaving group leaves first. That gives us a stable, tertiary, planar, sp2 hybridized carbocation, which means that the nucleophile can add from the top face or the bottom face, which means we get both stereochemical outcomes. These are formed in equal proportions. There's no reason why the nucleophile would want to add from the top of the planar cation rather than the bottom. Equal. So SN1 works on secondary and tertiary substrates. We need to add, however, an ionizing agent. We need a little bit of help kind of coaxing this chlorine to leave on its own. And for that, we use a polar solvent that stabilizes the carbocations. We can also use silver halide, so AgCl or AgBr, Silver is an ionizing agent, and it really is good at stabilizing ions. Also, heat will do this. Just simply adding heat helps us get over the energy of activation that's required for this chlorine to leave. So it works on secondary and tertiary. Remember that SN2 worked on methyl, primary, and secondary. So, and secondary in the case of SN2 was really kind of the extreme end. So secondary works for both. Tertiary only works in SN1. Methyl and primary only work for SN2. So remember, why doesn't SN1 work for methyl and primary? It's because the carbocation that would form if the leaving group were to leave on its own would be too unstable. We get a mixture of products. We call that racemization. We get products that look like they were formed by inversion and retention. I just want to clarify here. Remember I said this product, the retention product, the product where we retain our stereochemistry, this is R in our reactant, it's R in our product. This is not the result of front side attack. It looks like it would be. If front side attack were possible, this would be the product. But front side attack is not possible. If you go back and look at our SN2 diagrams, you will see that front side attack would involve the nucleophile approaching a carbon from the side that contains a negative leaving group. It wouldn't approach from that side. Front side attack does not work. So front side attack does not work, so this product is not formed by front side attack. It is formed by adding to a planar carbocation. It's formed in an SN1 mechanism, not an SN2 mechanism. Remember I said that SN1 will work, where SN2 does not work. Because we no longer require the ability to access the antibonding orbital of the chlorine, in this case it's chlorine, this chlorine is leaving on its own, which means that there's no longer an antibonding orbital. The nucleophile does not need to look for an antibonding orbital. In fact, what it does need to access is a big unhybridized p orbital. The empty orbital on a cation, sp2 cation, is a p orbital. It's a pretty big empty orbital. So we no longer need small nucleophiles. We can use bulkier nucleophiles if we want, because the carbocation is not hindered in the same way that an antibonding orbital would be hindered. So if our nucleophile is big and bulky, it wouldn't do SN2. It could do SN1 if we could coax our leaving group to leave first, meaning if it's secondary or tertiary, and we can use an ionizing agent. There's one more facet of SN1 reactions that are unique to SN1 and impossible in SN2. Look what's going on here. Here we've got a substrate with a leaving group. Here's our chlorine. Now, think about it from the perspective of the leaving group. What's the substitution of this carbon? Is it methyl, primary, secondary, or tertiary? It's secondary. It's got one carbon here on the ethyl group and a second carbon here on the tert-butyl group. So secondary means that we can do SN2 or SN1. We could do SN2 if our nucleophile is small enough. This is a pretty small nucleophile. We've already mentioned that methoxide is a nucleophile that can participate in SN2 reactions. So secondary means SN1 and SN2 are in play. Small nucleophile means SN1 or SN2 are in play. You don't have to have a bulky nucleophile to do SN1. You can though. You do have to have a small nucleophile for SN2. So based on our substrate and based on our nucleophile, we have SN1 or SN2 possible, both of them. We're using a polar aprotic solvent, also good for both of them. But we're also including ionizing agents, silver chloride and heat. So these reagents are going to tip the scale in favor of the SN1 mechanism. Let's look at the product. This is very interesting. What's wrong with our product? Notice that the nucleophile, our OCH3 group, has gone on to a carbon that did not bear the chlorine. That's impossible if this were an SN2 reaction. Remember, in an SN2 reaction, the nucleophile attacks the carbon with the leaving group and the leaving group goes off. So in an SN2 reaction, the nucleophile will always be on the carbon that had the leaving group. That's not the case here. In fact, not only has the nucleophile gone on to the wrong carbon, but we've moved a methyl group. We have 3 methyl groups on this carbon here in the reactant. One of those methyl groups has migrated over to the first carbon that had the chlorine on it. This is called a rearrangement, and it is possible with SN1 mechanisms. Here's how it happens. Since it's an SN1 mechanism, the first step would involve the leaving group leaving. That generates, in this case, a secondary cation. This carbocation is secondary. It's got the ethyl group and it's got the T-butyl group. This then undergoes what we call a methyl shift. One of these 3 methyl groups literally migrates over. It kind of just shifts over. It takes its electrons and lets go of this carbon and grabs the next carbon over. Now, when that happens, something very important occurs. This carbon that's got the cation gets a 4th bond. It's gaining a bond as a result of this methyl group moving over. But this carbon that loses the methyl group ends up with the cation. And look what happens. This cation is secondary. This cation is tertiary. We have increased the stability of the cation as a result of doing this methyl shift. Once we've formed this tertiary cation, then the nucleophile will add in. Therefore, we get that product. We get the rearranged product. A good question would be, why does the nucleophile add to the tertiary, but not the secondary? And the answer is that because the tertiary is so much more stable, it is around for much longer. As soon as the chlorine leaves, remember that in the SN1 reaction, the leaving group leaving is the rate limiting step. That first step is the rate limiting step. So this step is very slow. As soon as we make that secondary cation, we immediately do a methyl shift and we get to the tertiary. So the tertiary will be around much longer than the secondary. So we simply have much more likelihood of a nucleophile finding a tertiary than it would finding the secondary. That's called a methyl shift. And a methyl shift would only happen if the cation will increase in stability. So we could go from a secondary to a tertiary, or maybe from a secondary to a resonance stabilized cation, or from a tertiary to a resonance stabilized, like an allylic cation or a benzylic cation. Theoretically, if we could make a primary cation, it would shift to make a secondary or shift to make a tertiary if possible. But the likelihood of making the primary cation in the first place, remember, is very low. So usually we're going to be looking for a secondary to a tertiary shift, or a secondary to a resonance stabilized shift, or perhaps from a tertiary to a resonance stabilized shift. In this example, we're moving a methyl group. You can also move a hydride, move an H. Imagine that this was an H instead of a methyl. We could move that H over and we would still have a tertiary carbocation. This would be an H over here instead of a methyl then. So that's SN1. Your book has this nice table that compares SN1 to SN2. This table should summarize all of the points that we've made so far. Let's start with SN2. SN2, we need a strong nucleophile. We need a small nucleophile that can access that antibonding orbital and force off that leaving group. With SN1, you do not need that strong of a nucleophile. You can get away with using weak nucleophiles. That means they can be bulkier, and they need not be as negatively charged. Just to show you why, in an SN1, the nucleophile adds to a positive charge. In an SN2, remember, the nucleophile only added to a partially positive charge. The nucleophile is adding to a partially positive charge. So for SN2, the nucleophile needs to be very negatively charged so that it can generate enough attraction to a partial positive charge. In SN1, we are generating a full positive charge. So our nucleophile does not really need to be negative. It could be neutral. Negative obviously would work just fine, like I'm showing you here, but we could get away with a neutral nucleophile or a bulky nucleophile. So strong nucleophiles are what we need for SN2. We can get away with weaker ones for SN1. SN2 works on methyl, primary, and a little bit of secondary. Secondary will work as long as our nucleophile is small enough. With SN1, we can get away with tertiary, and secondary works as well. Solvent for SN1, we need a good ionizing solvent. We need something to help promote that first step where the leaving group leaves on its own and we generate a cation. With SN2, we don't necessarily need that. We can use a wider variety of solvents. In both cases, we need a good leaving group. We need the leaving group to be good enough to be forced off by the nucleophile in the case of SN2, or to be able to leave on its own, to be good enough to leave on its own in SN1. So we always need a good leaving group. Other notes, this says silver nitrate. I have just mentioned silver, silver chloride, silver bromide, silver nitrate. Any kind of silver ion will induce ionization as well as heat. SN2 is second order. Its rate depends upon the concentration of the substrate and the nucleophile, because the mechanism is only one step, and that one step involves both of those species. For SN1, the rate limiting step is the first step, and that first step only involves the substrate. It does not involve the leaving group. So it's first order kinetics versus second order kinetics. The stereochemistry, we get a mixture because the nucleophile can add from either side of the carbocation once the leaving group has left. In SN2, we always get inversion. In SN2, our only option is to add the nucleophile from the backside. So we will always invert our stereocenter. rearrangements are common for SN1 because you are generating carbocations. Anytime you generate a carbocation, you have to analyze the structure to determine if a shift, if a methyl shift or a hydride shift would increase the stability of the carbocation. And if the stability of the carbocation could increase as a result of that, the shift will occur. One thing I didn't mention, shifts only occur really one spot. So this methyl group is moving over one carbon. Shifts really don't often occur moving 2 or more spaces. So they can only move to one adjacent spot. But rearrangements are possible and fairly common for SN1. They are impossible for SN2. So please study these. Make sure you understand all the factors that can cause mechanisms to go one way, SN1 let's say, or another way, SN2. Sometimes there will be conditions where both can happen. You might get SN2 pathways occurring alongside SN1 pathways. Notice in this table, a good guide is to learn SN2 and understand that anytime SN2 cannot occur, SN1 can. If your nucleophile is not strong, SN1 can do it. If your substrate is too bulky, your SN1 can do it. If you have ionization or ionizing factors, SN1 will work. Anytime SN2 does not work, SN1 will. So that's all for lecture 8. The workshop in our Stromanis chapter is 13. Chapter 13, Chem Activity 13 in Stromanis. Again, the chapter in Wade is chapter 6. It's the first part of chapter 6. So if you want to go back and look at the notes in Wade, you can do that.